Hello, friends. We are here to see the second session of actuarial statistics. In the previous session, we saw the need of insurance in the society, why people need insurance, and how insurance works. In simple way, we have seen. For instance, the company which provides insurance to people is called as insurer, and the one who buys the insurance product is known as insured. Insurance is required because there is uncertainty in life. In life insurance, we talk about the life of a person, the life length of a person, mainly the bread earner of the family. So family depends on the main earner of the family, and therefore it is very crucial for the bread earner to survive long so as to protect and feed the family members. In order to ensure that this happens continuously, people buy life insurance. Now, although death is a certain event, means death occurs with probability 1. One day or the other, every person is going to die. What is uncertain about death is when it is going to happen. That is mainly when the person's life ends. That is what is not known to people. And therefore, there is a variation in people's life length. So we treat the life length as a random variable. In statistics, the life length is the person's total years spent on the planet. So, age at which an individual will die, this cannot be predicted. So, the total life length or actual age of the person when he dies is known as the lifetime, and that is called as a random variable. In statistics, a variable takes different values. It is not constant. If suppose age of people would have been constant, that means everybody who is born spends say 80 years of life and then dies at the age of 80, then there would not have been statistics and there would not have been insurance as far as the life length is concerned. But we know that that doesn't happen, and therefore we have to consider it as a random variable. So, in order to study the life length of the person, we denote it by the notation x, which is generally used for the random variable. Now, this is a continuous random variable. Even though we talk about in terms of years, actual time spent can be a continuous random variable. It is taking non-negative values also, that is, it is always greater than 0, and therefore now we are in search of different models for the life length. As you all know, that in statistics we talk about different distributions. Now, what are these distributions? These distributions are nothing but the different statistical models. Means, when we want to quantify the uncertainty, we talk about probability. Probability is the quantification of the uncertainty we are considering. So, what is the probability that a person whose today's age is 60 will die in the next 5 years? That is the question we want to ask ourselves. So, that means we are talking about the probability distribution. You know that the total probability is equal to 1. So, how is this total probability distributed over the range of the variable, that is life length? That is what we are talking about. So, which is a suitable model for the life length random variable? That is the key question one has to answer. The simplest model one can think of is uniform 0, 1, 100, considering that a person maximum life could be 100 years. Okay, then which are other models that we can think of? They should be negative, non-negative, and they should be continuous. So, another model that comes to our mind is exponential, gamma, Weibull, and there are other models as well. All these are statistical distributions. Now, if we choose one of these as models for the life length of a person, suppose we begin with uniform 0, 100, then you know the probability distribution or the PDF is 1 upon b minus a. F of x is 1 upon b minus a if it is uniform over a to b. Therefore, probability that the life length is between 10 to 20 years would be 1 upon 20 minus 10, that is 1 upon 10. Similarly, if we consider the probability that the person dies between age 80 to 90, that is also 1 by 10. So this is somewhat not correct, right? Because probability of death in the age group 10 to 20 is the same as the probability of death in the age group 80 to 90. But we know that as age increases, the pressure of mortality, this is the word that we use in insurance for death, the pressure of mortality increases. So, definitely, these two probabilities cannot be the same, and therefore, this uniform 0 to 100 model is not a good choice. Suppose we consider another model, that is exponential distribution, then the x, that is the total life length, follows exponential with say parameter mu. Now, what is this Tx? Even though it is introduced here right away, it is nothing but the life length of the person whose current age is x. For instance, if suppose a person is of 60 years of age, then x is equal to 60 here. So, if the total life length, that is from birth to death, that is x, and t of x is from x to death, okay. So, if the total life length is exponential with parameter mu, then t of x, one can also show it theoretically that this is called as the remaining lifetime after attaining the age x, that is also distributed exponentially with parameter mu. Why this happens? This happens because of the forgetfulness property of exponential distribution, or memoryless property, or constant hazard, all mean the same. So, therefore, this is again not correct because the remaining lifetime after attaining age X should be different, isn't it? Should be differently distributed. And therefore, this is also not a good choice. So, therefore, uniform and exponential both are ruled out as far as the human lifetime is concerned. You know that in case of reliability, this exponential distribution works well whenever there is constant hazard. With electronic components, probability of its breaking any time is the same. Even if you buy it today and it breaks, the vendor will say that, oh, it's electronic item, it can break any time with same probability. Therefore, But with human life, it is not correct. Okay, so distribution of T of x is the conditional distribution of x minus x given x greater than x. This sentence saying capital X is the total lifetime, small x is the attained age. So x minus x is our T of x, the remaining lifetime. Okay, so this remaining lifetime, given that x is greater than x, given that you have attained age x, now how much is remaining? That is what the insurance people are interested in. Because a person who is alive, that person only will go and buy the insurance, isn't it? So that person whose current age is X, and he is going for an insurance product. Okay, so let us understand this notation. T30. What is the T30? T30 means the remaining lifetime of a person whose current age is 30. T20, T80 is the remaining lifetime of the person whose current age is 80 years. So, in case of exponential distribution, what happens? The T30 and T80, both the lifetimes distribution remain the same. So, that is ridiculous. Okay. Another choice was a Weibull distribution. Now, this Weibull distribution, it's okay, but the problem is that for any combination of parameters, it does not cover the lifespan of 100 years. And then, so people who are going till 100 years in their life, they will not be modeled by the Weibull distribution. So these are some shortfalls of of these different models, statistical distributions. So basically, the support, that means the range of the values that the random variable takes, should be from say 0 to 100 or 110 or 115. We have heard that the maximum recorded lifetime is 122. If you have seen that movie 102 Not Out, there they specify that so far 122 is a recorded. There could be more people also who have crossed 122 years of life, but they are not recorded. That's why they are not considered. Anyway, so support should be at least up to 100. Then only it makes sense. And another thing that the model should take care of is that the rate of mortality should increase as age increases. If it is not doing that, then that model cannot be a good model. Okay. Now, there were other people who were mathematicians. They were not statisticians, or for that matter, that time statistics was not considered as a branch, even though some inventions had made by that time in the 18th century, like normal distribution and all. But these people were mathematicians, and they were looking at the people's live data. So they thought of something different. They did not consider this lifetime as a random variable, or I mean, they will not. They did not focus it on the right time random variable per se, but they thought about the force of mortality. So, force of mortality is like instantaneous derivative. One can say like that. So, force of mortality is given by mu x, which is fx divided by sx. Now, with the statistics notation, but they did not have this fx divided by sx. Benjamin Gompertz, this person suggested the force of mortality to be modeled by bc raised to x, and this was a derivative, or of the concept that the mortality is proportional to age, and on the basis of that this differential equation was solved, and mu x is equal to bc raised to x. That is the model thought of by Benjamin Gompertz, who was an actuary in London. Now, what does this mean? This b greater than 0 means that it is increasing. X age is here, c raised to x. So it increases, so to say, exponentially with the parameter c, which is greater than 1. X is obviously greater than or equal to 0, being age of the person. Okay, now if we think that this force of mortality is like instantaneous derivative, then we can consider it with the model of statistical model as the PDF divided by survival function. PDF of a continuous random variable f of x, you know that it is not probability, but if you say fx dx with small dx added to that, then it becomes the probability of x lying between, say, x to x plus dx. Okay, so f of x, so to say, is the probability of a very, very tiny interval and then divided by Sx. Sx is the survival function, that means probability capital X greater than or equal to X. Total lifetime greater than or equal to small x means that person has already attained the age X. Conditional on that, what is the probability that he will die in the smallest interval x to x plus dx, that means at x. That means it is the ux is nothing but, in simple words, could be thought of as the probability of dying at age x, given that that person has lived up to age x. Now, this particular mu x is modeled by bc raised to x. This is the Gompertz curve or Gompertz model. When you decipher this statistically and then find out the survival function with this formula, it comes out to be survival function as e raised to minus m c raised to x minus 1, where m is equal to b upon log of c to the base e, and the value of c is being usually being between 1.07 and 1.12. So this was good enough because it could model the increasing nature of the risk of dying with age. But the problem with that, or not the problem, but a modification to that is suggested by McKeham's law, that some people die in accidents. They die due to chance. That is not related to the age. So the cause of death is not always related to death. Most of the times it is related to age, but sometimes it could be related to any random cause. So that random cause, in order to consider in the model, this McKeham's suggested to add one constant A to that model, and then it became the mu x is equal to a plus bc raised to x. So these are the two models which are provided by Gompertz and McKeham, and they are still used in actuarial science and actuarial statistics. So this is a comparative picture of different models. So Gompertz, if you see that this slowly increases with age, force of mortality slowly increases with age, and after 60 it increases steeply, and beyond 80 it increases very, very steeply. Okay, and then this McKeham's also similar, but with some threshold to that. So this kind of situation is seen in these different models that we saw in this